A very simple example is the case of the hybridization of an s orbital and one p orbital. For example, the 2s orbital of carbon and see 2p orbital of carbon, if we take the linear combination of this, it will be, if we take them to be approximately the same, it is 1 by root 2 phi 2s plus phi 2p, okay. And the antilinear combination is phi 2s minus phi 2p. Okay. Now, this is the redefined atomic orbital. This is not a molecular orbital. This is a redefined atomic orbital, taking into account that the 2s orbital and 2p orbitals of the carbon atom are not too far away in energy, and therefore may contribute to bonding simultaneously being present, and this is the simultaneous presence of both the atomic orbitals phi s and phi 2p, which of course now you call this as psi of carbon. And for example, if this forms a bond with hydrogen, as in the case of acetylene with psi of hydrogen, which is usually written as phi of 1 s of hydrogen. Now, this is this linear combination with plus 1 s, it gives you a molecular orbital. The nature of these bonds phi s and phi 2p, if you draw the s orbital, is somewhat spherical in nature, and the 2p orbital, assuming that it is along the bond axis on which the carbon bond is formed, the 2p orbital, if you take the 2p orbital, it is plus, and there is a minus along the bond axis, plus and minus. If you take the sum of these two, essentially what you get is an orbital which is more towards the other carbon atom, plus and minus, and the same thing with this carbon. If you do for the acetylene case, you see that this is overlapping with plus and minus. So, this is a C bond, as it is in the case of C2H2. Okay. So, what you have done is basically taking a linear combination of the s and p orbitals of one carbon atom, and since there is no difference between the other carbon atom, you take the same linear combination there, and this linear combination gives you what is called the molecular orbital. So, you have CsP of carbon 1 plus CsP of carbon 2, and this one is phi, what we have written down, phi 2s plus 2p, 1 by root 2 phi 2s plus phi 2p. So, taking the positive linear combination gives you the bonding orbital, taking the negative linear combination, this one, gives you the anti-bonding orbital. This is called the sp hybrid orbital. The hybrid orbital is still an atomic orbital. It gives us a physical picture in realizing that C2H2 is a linear molecule, and therefore, the carbon hydrogen carbon, that is in the same axis. That is possible only if the p orbitals of that, the two carbons overlap with each other, but p orbitals and s orbitals being not very different in energies, it is possible that the two combine to give an effective atomic orbital which is directed towards the bond axis, and likewise the other which is directed towards that bond axis, the two overlap to give you. What about if you do S2p, 1 s orbital phi 2s plus phi 2pz, say plus phi 2px. It is possible to take a linear combination of these three in three different ways to form what are called three mutually orthogonal atomic orbitals. Mutually orthogonal atomic orbitals. and these are called psi 1, psi 2, psi 3 if you want to, you label them as 3 combinations, and these form a bond with the hydrogen of or carbon or any other atom, that is called sp2 hybridization. Yeah. The 3 wave functions are psi 1, 1 by root 3 phi 2 p s plus root 2 by 3 phi 2 p z. Psi 2 is 1 by root 3 phi 2 p s minus 1 by root 6 phi 2 p z plus 1 by root 2 phi 2 p x, and psi 3 is 1 by root 3 phi 2 p s minus 1 by root 6 phi 2 p z minus 1 by root 2 phi 2 p x. These 3 orbitals, if we look at it carefully and if we are able to actually add them mathematically and plot them, you will see that they are actually directed at 120 degrees to each other. 120, 120, 120 degrees. Okay. Assuming that the center of mass and an x, y, z axis system, if you do that x, y, z axis system, okay, you would see that these 3 orbitals are actually directed along the 3 corners of an equilateral triangle, and that is very important because the resonance, the structure of ethylene, for example, if you want to understand the bond angles between the hydrogen carbon carbon, this is 120 degrees, this is 120 degrees, and this is 120 degrees, and there is no way that you can understand in a very simple picture this directed, spatially directed bond formation, except taking into account the atomic orbital itself as a hybrid combination of the s and p orbitals, with the simple fact that the s and p orbitals are obviously not very different in energy. So, this is essentially called the sp2 hybridization, and what happens is these 3 orbitals are now combined, these 3 orbitals are now combined with the hydrogen atom or the carbon atom, as the case may be, to form the 3 molecular orbitals. Therefore, again these are atomic orbitals only, but hybridized. Hybrid. The last of this in this lecture series is the most famous one, namely the hybrid combination for involving all the s and the p orbitals, 3 p orbitals, almost with equal weighting. Therefore, you would write psi 1 as phi 2 s plus phi 2 p x plus phi 2 p y plus phi 2 p z, the normalization constant 1 by 2, and the second linear combination phi 2 s plus phi 2 p x minus phi 2 p y minus phi 2 p z, psi 3 as phi 2 s minus phi 2 p x minus phi 2 p y plus phi 2 p z, all 1 by 2 as normalization, and then psi 4 as phi 2 s minus phi 2 p x plus phi 2 p y minus phi 2 p z. 1 by 2. So, the way this linear combination is done using all the 4 orbitals of the principal quantum number n with equal weightage is to ensure that these orbitals are orthogonal to each other. You can see that right away. Phi 2 s square integrated over the all volumes, this will give you 1. Phi 2 p x square integrated over all the space will give you 1, but this will give you phi 2 p y square has a minus sign, phi 2 p z square has a minus sign. So, this will be 1 plus 1 plus minus 1 plus minus 1 times 1 by 4, and this will be 0. And likewise, you can see that there are 2 pluses and 2 minuses, therefore, any pair of the atomic orbital will any pair of this will be orthogonal to each other. Why did we not put the sign on phi 2 s? We all know that phi 2 s is spherically symmetric, and it is a p orbital which has a plus and minus low. Therefore, in taking the linear combination, the overall sign of the wave function also does not matter. Therefore, if you keep the 2 s as positive, you must choose 2 of the other 2 p orbitals as negative. This is directed in space. The linear combinations can be given from the tetrahedron. You can see the tetrahedron is from connecting the face diagonal points. Let us do the following. The face diagonal points, if we connect to these, and the corresponding face diagonal points are these. Okay. If we connect this to the body center, you can see this is, if you draw the x axis towards us and the y axis and the z axis, this vector is generated by adding phi 2 s with the 3 positive combinations phi 2 p x plus phi 2 p y plus phi 2 p z, because all the 3, the x axis is this way, the y axis is this way, the z axis is this way. Therefore, this vector has positive x and y and z components. So, this is the linear combination which is pointing in this direction. Okay. Now, what about the face diagonal which is pointing in this direction? If you look at it carefully, that has a negative y axis combination and a negative x axis combination. Therefore, this particular blue is phi 2 s minus phi 2 p x minus phi 2 p y plus phi 2 p z. The z is positive because z is up is positive. Now, what about this combination? If you look at it carefully, the y is positive because, sorry, the x is positive here because the x is in this direction towards us. Therefore, the x is positive, but the y is negative and the z is negative. Therefore, that combination is phi 2 s plus phi 2 p x minus phi 2 p y minus phi 2 p z. And the last one you can see immediately is the fourth one, namely phi 2 s, we have minus 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 minus, therefore, we have minus phi 2 p x plus phi 2 p y minus phi 2 p z. Okay. Yeah, this is on the y axis is this combination. This is the positive y axis, the negative x axis, let us see, minus minus minus, and the 2pz is the z is also negative. Therefore, you see these two are negative. Therefore, you see that the 4 orbitals psi 1, psi 2, psi 3, psi 4, all of them point in the corners towards the corners of a perfect tetrahedron, and this will form a bond with the hydrogen or chlorine or any other to form what is known as an sp3 hybrid orbital plus atomic orbital to form a molecular orbital. The hybridization is a sort of a physical structure, physical picture in mind to understand what is meant by the directionality of the orbitals, the atomic orbitals. In the modern language, of course, hybridization is not really required, because we take anyway linear combinations of all atomic orbitals of all atoms. In fact, we do not even use the atomic orbitals, we use Gaussian orbitals. Therefore, the picture of hybridization was a very nice physical idea to understand directionality up to a point of time. Today, we simply ask what is the percentage contribution of a certain orbital component and so on, and therefore, the sp, sp2, sp3 d, sp2 or sp2d, d2 sp3 or sp3d. This qualitative picture of hybridization is very easily understood by taking the linear combinations of the atomic orbitals of all the atoms, assuming they all behave like the hydrogen atom atomic orbitals. That is a fundamental flaw in the whole process anyway, is the understanding that all atomic orbitals are like the 1s, 2p, 2s orbitals of the hydrogen atom. They are not. The moment you have an additional electron, this picture is gone, but this is a very good and reasonably approximate picture for us to draw qualitative diagrams and to understand generally the chemistry around it. The more serious molecular orbital theory or more serious valence bond theory will have to be done only computationally, and that is not part of this course. Therefore, I hope I have introduced you to some very elementary, still useful and pictorial representations of chemical bonding that Lewis and Linus Pauling and many others had in the form of a simple molecular orbital picture. We will stop with this, and in the next set of lectures we will talk about one particular case of what is called the chemical bonding or the molecular orbital theory in conjugated systems or alternate single double bond systems, and also cyclic systems such as benzene. With that, we will end this particular course on chemical bonding. We will meet again with the Huckel's theory for the molecular orbitals of conjugated systems. Until then, thank you very much.